All right, so we're going to look at indeterminate forms and L'Hopital rule. Now the question is, what do we mean by indeterminate forms and why do we need L'Hopital rule? All right, so let's start by looking at this function then. All right, the first thing everyone can see is it is undefined when x equals to 1. That is very obvious. So now let's look at what happens when x gets close to 1. So we look at limits as x approaches 1 of this function. You can see clearly it's difficult to compute this limit, all right? Because you have a lean function there at the top and you have x minus 1 at the bottom. So most of the method that I've showed you before, it doesn't work here, all right? So clearly it brings us to the idea that we need to come up with another technique of solving this kind of limit. All right, so the first thing we're going to observe is, remember in the previous function I showed you, if I plug in x equals to 1 at the top of the bottom, ln of 1 is 0 and 1 minus 1 is 0. So we're looking at something that looks like this, all right? Indeterminate form of type 0 over 0, all right? You have a function over a function where the limit of the top function gives you 0, the limit of the bottom function gives you 0. We call that indeterminate form of type 0 over 0, all right? Now let's look at this closely. Before, if I give you some rational function like this, if you plug in 1 at the top or the bottom, obviously you get 0 over 0. But that doesn't make sense, right? Because I taught you that you need to follow all the steps. Direct substitution, if it doesn't work, you try to factorize. If it doesn't work, you try to rationalize, especially if it's a root function, and so on. I've shown you so many methods, all right? Now, for a case like this, if you factorize, obviously see, there's a factor there that will cancel with another factor there at the bottom, and it simplify gives you an answer, all right? We've also seen for the sine function, so limit as x tends to 0 of sine over x is 1, that was a special limit. You see that also you get 0 over 0, but then you get 1, all right? So don't just do direct substitution. You need to, first of all, exhaust all the methods that I've showed you before, and if none of those methods work, then before you can go ahead and treat it as an indeterminate form and hence apply L'Hopital rule. Again, if we come back to this function, notice there's just nothing you can do because there you get naught over naught, and the only way to solve this is what we call L'Hopital rule. All right, I'm going to explain what L'Hopital rule is in a moment. All right, and if we look at the horizontal asymptote of this function, so horizontal asymptote, remember if I say find the horizontal asymptote of a function, we're looking at the limit as x approaches infinity. All right. And the reason I'm not using plus or minus infinity in this case, because remember that there's a little bit of restriction there on the ln x, all right? But anyways, limit as x approaches infinity, that is gives you the horizontal asymptote. And again, at the top here, as x approaches infinity, what happens? The ln function goes to infinity. And then as x approaches x minus 1, and so the limit as x approaches infinity of x minus 1, again, it's just infinity, right? You get infinity over infinity. So this is another indeterminate form because infinity over infinity doesn't give you an answer, right? It's just infinity. So we call this indeterminate form infinity over infinity, right? So L'Hopital rule works when you get indeterminate form 0 over 0 and when you get infinity over infinity, or we can say plus or minus infinity over plus or minus infinity. And just to mention, if you choose to take the limit as x approaches minus infinity of this ln function, remember the ln function looks like you have 1 there and you have something that looks like this, all right? So that's typically your ln function. As you're heading towards infinity, as x is going towards infinity, notice it, this function goes towards infinity. And now look at what happens. So x cannot go towards negative infinity because ln up a negative number does not exist. All right. I hope that clarifies the statement there. All right. Because horizontal asymptote, like I said, we always check for limit as x approaches plus or minus infinity. In this case, we stick to positive infinity. All right, so we've seen another indeterminate form, which is infinity over infinity. So we've seen two types, so 0 over 0, and we've seen plus or minus infinity over plus or minus infinity. All right. And let's see how we can solve this. So suppose they give you something like this, and I ask you to evaluate this limit. Obviously, you know what to do. You divide by the highest power of x that occurs at the denominator. All right, you've seen that already. That's how we found horizontal asymptote. Divided by the highest power of x that appears at the denominator. So in this case, it's going to be x squared. All right, if you look at the bottom there. If you divide all two, you simplify, you get a half. All right. So don't be blind and just say, oh, if I put infinity at the top at the bottom, I get infinity over infinity. Therefore, it's L'Hopital. No, it doesn't work like that. All right. Now, this is what L'Hopital says. So if you have the limit as x approaches AF of x gives you 0, and g of x also gives you 0, or f of x they give you plus or minus infinity, and the limit of g of x gives you plus or minus infinity, then you end up with indeterminate forms that look like this. So 0 by 0, or let's say plus or minus infinity by plus or minus infinity. Then this limit that I asked you, you can write it as the limit as x approaches a of first derivative of f function divided by first derivative of the g function. So once your limit satisfy the indeterminate type 0 over 0 or infinity over infinity, you can go ahead and differentiate the top function and the bottom function, right? And once you differentiate that, it will make it much easier, and most of the time, the limit will not give you an answer. Sometimes you have to keep doing that again and again up to when you get to a final answer. All right. Is there any question? I see someone raise your hand. Yes, any question?
Yes, sir.
Okay, go ahead with your question.
Yes, slide, sir.
All right, the previous slide, that was, yes.
In a
Okay.
test situation, what if I just choose to take the numbers which have x with the highest exponent, and then just like if I would say x squared over 2x, and then carry over x squared over 2x squared, and carry on with the calculation from there, rather than just dividing by the highest rather than dividing by x squared everywhere.
All right. People do that, but you need to be careful because then you changing the question. All right. Although your answer will be
Yes, sir.
correct, but the method is going to be wrong, because if I choose to just focus on these two guys here and ignore this minus one at the top, minus at the bottom, I'm changing the function. So I'm saying that my f of x function is now x squared and g of x is 2x squared. All right. If you do that, so let's say you just write this whole thing here, you say it's equals to half, whereas you just divided x squared over 2x squared. Yes, your answer is correct, but then in terms of method, Mike, I need to see this, all right? So the only acceptable method for you to have full marks when I ask you for horizontal asymptote is to divide all two by the highest power of x, all right, just to be safe. Because, like I mentioned again, x squared over
Okay, sir.
2x function completely is no longer the function that I initially asked you, all right? Does
Yes,
that
sir.
make sense?
It does.
Yes. So for a multiple choice, do that because you don't have to show any working for that. But definitely you get the correct answer. But if you have to show me your working, then you can't do that. You can't just say explore what you expect as your working. That is not going to happen. All right.
Yes, sir.
Okay, let's move on. We've seen what L'Hopital is. So let's do this example. Remember, we said this was a tough example because we didn't know what to do. So let's see, does it satisfy the condition? So how I expect you to solve this is to plug in 1 there at the top, ln of 1 is 0, 1 minus 1 is 0, and indicate in bracket that this is 0 over 0, right? So if you show me this, it means that you've identified the type. It's indeterminate. And you go ahead, you see here what they're doing, you differentiate the top function, you differentiate the bottom function. Very important, when you applying L'Hopital rule, please try and put a little LH there, all right? So to show me that you're doing L'Hopital. So whenever you're doing L'Hopital, please put an LH. Some people just prefer an H, but just write LH, all right, to tell me that you're doing L'Hopital, all right? Every time you apply L'Hopital, put LH. In a step like this where you've already differentiated, you see I don't put any LH here because obviously I'm not applying L'Hopital. L'Hopital is when I'm differentiating the top and the bottom, all right? And if you differentiate, you simplify, notice it, your limit not works, it gives you 1, right? Let's see another example. Right, this is another example. If you take the limit at x approaches infinity, if you put it there at the top, you get infinity, all right? The top there's infinity, at the bottom infinity, where you just get infinity. Again, this is an indeterminate form. Remember I told you, you can either get 0 over 0, or you can get plus or minus infinity over plus or minus infinity, all right? So any of those works. And the idea is, again, you can see that from the textbook, they don't put L'Hopital, but I'm telling you, please make sure you write the L'Hopital, all right? Put a little LH there, and tell me that you're doing L'Hopital by differentiating the top divided by the derivative of the bottom piece. If you do that, you see simplifies to this. And now if you substitute infinity again, see what happens? You see end up with infinity over infinity, all right? You see what's happening. You see have infinity over infinity. And if you keep going in that direction, so you apply another L'Hopital. So notice it here, we're doing L'Hopital again. I'll just indicate here. You differentiate e to the x, stays e to the x, you differentiate 2x now, you get 2. You see, I've done L'Hopital twice, all right? And now it becomes very obvious, the top is infinity, but the bottom is the constant is 2. Therefore, your answer is infinity, means that limit does not exist, all right? So you see, you need to prove beyond reasonable doubt that a limit does not exist by applying L'Hopital as many times as possible, as long as it satisfies that condition, all right? And please, at every stage, indicate the indeterminate form that you solve. Don't just go ahead and be differentiating. You need to be able to tell me that this is an indeterminate form. All right, another example is ln x over root of x, right? Again, we start by identifying the form. So before I even do L'Hopital, let's identify the form. As x goes towards infinity, ln of x, obviously get infinity. Root of x also you get infinity. So the indeterminate form there is infinity over infinity. I can go ahead and say LH, I apply L'Hopital. The LH I write it on top of the equality sign, and I differentiate the top and I differentiate the bottom. You see I simplifying there. And then I try to substitute again as x goes to infinity. Remember 1 over infinity 0 and 1 over 2 root x. You get 0 over 0. You see now you're getting a new type, which is 0 over 0. So you move from infinity over infinity to 0 over 0. Again, what do you need to do? You need to do another L'Hopital. So we now adapt to do L'Hopital. Remember here we also did L'Hopital, so I'm just going to put LH there. So we did L'Hopital the first time, and we got this, and we got the new type indeterminate form, which was 0 over 0. Do L'Hopital again, now you get 2 over root of x, and as x approaches infinity, 2 over some infinitely large value, you just get 0. Right, there we go, you're done. You see, we also had to do L'Hopital twice in this case. And let's look at this one. You have 10x minus 1 over x cubed. Obviously, everyone by now understand the routine process. You're going to put in 0, 10 of 0 is 0, 0 minus 0 is 0. So the indeterminate type is 0 over 0. So it qualifies for L'Hopital rule. And if you notice it, yeah, they're doing L'Hopital. All right, it's not clear enough, and make sure you download the lecture slide so that you can see clear. You get 6 squared minus 1 over 3x squared. And if you plug in 0 again, you end up getting, remember 6 squared of 0 is just 1 over cos of 0 is just 1, all right? And 1 minus 1 is 0. You still end up with 0 over 0. So you need to still apply L'Hopital. So this is still applying L'Hopital. You end up getting 2 6 squared times x over 6x. Let me try to zoom this out a little bit because this example is very exciting. All right, I hope you guys can see it after zooming in. So what happened is sometimes you need to think. All right, you need to think nicely because the second time I apply L'Hopital rule, I end up with limit as x tends to 0 of 2 sec squared x tan x over 6x. Now, I know the result for the limit as x tends to 0 of 2 sec squared. All right. And tan x over x will just be 0 by 0, which qualifies for L'Hopital rule. Be careful if you put everything together, so you try to measure the sec squared and tan x and the 6x, you have to differentiate very complex function. It means you'll be applying some sort of product rule and chain rule, all right, which is too much work. So it's better that I split the limit into two. So I start by saying limit as x tends to 0 of 2 sec squared x over 6, which is what you see there. So remember, you can take the constants in front of the limit, so you just get 1 over 3, limit as x tends to 0 of sec squared x, and then I isolate the other limit, which is limit as x tends to 0 of tan x over x. Now, this second limit, the first limit gives me a valid answer. We know it's going to be 1/3 times 1. But the second limit here, so this limit here, qualifies for L'Hopital rule because you get 0 over 0. So all I have to do now is to differentiate the tan x over x. So differentiate tan x, you get 6 squared x. And if you differentiate the x, you get 1. And if you do the entire limit, you just end up with 1 over 3. All right. So save yourself the whole work, because if you didn't split the limit into two, if one limit is known, please isolate that limit and then work with the other limit that gives you L'Hopital rule. All right. Because if you put everything together, you'll be doing product rules. So if you had to differentiate this sec squared times tan squared, it's going to be some other really complex function that you might keep differentiating forever, right? So once I ask you a question and you differentiate and it keeps going in a cycle, it means it's never ending, you never get into an answer. It means that you fail to actually point out some important uh, observation. All right, so you need to look at it closely and see what can I isolate that's going to give me an answer and what other function is going to be left so that I can now apply my L'Hopital rule. All right. Let's look at example 5. Example 5. Now that we've done L'Hopital, I know most of you in your mind is, I'm going to differentiate the top and the bottom. But be careful before you differentiate. Try and see if the rest of the tissue actually works. So if I put pi there, sine of pi is 0. At the bottom, you have 1 minus cos of pi is minus 1. So it's 0 over 2. The answer is 0. So this 1 here simply gives you 2. No, it gives you 0 over 2, which is just equal to 0. So this one simply gives you 0 over 2, which is 0, all right? There's no L'Hopital rule here, all right? Because most of you end up falling in the trap that, maybe cos pi is 1, and they're trying to test us L'Hopital here. No, if I ask you a question, follow all the procedures, all right? Start with direct substitution. You see in this case, direct substitution work. Sine of pi gives me 0. 1 minus cos of pi is just 2, 0 over 3, 0. And you see here, this solution is for the people that blindly apply L'Hopital whenever they say limit. All right, which is wrong, completely wrong. All right, do your direct substitution, you get 0 over 2, which is 0. Now let's look at something called indeterminate product. All right, we've seen indeterminate forms, indeterminate quotient, which is the limit as x tends to a of some f of x over g of x. Now looking at indeterminate product, where we're looking at the limit as x tends to a of f of x times g of x. All right. Let's see how that works. So in this case, this is where your focus is. All right. You want to get to this step. So when you do your limit, one of them is 0 and the other is infinity. All right. We call this indeterminate product. So indeterminate product only works for 0 times plus or minus infinity. All right. So you know you have an indeterminate product. Please don't tell me that 0 times infinity is just equal to 0, because some of you do that. Sometimes it might give you 0, and sometimes it might give you an actual answer. All right. You see here, that's what they're trying to tell you. Sometimes your answer they might just be 0. Sometimes you might just end up getting infinity, and sometimes you might just end up having a different answer. All right. So let's see what the possibilities are. And the secret here for indeterminate product is if I get f times g, where one of them, when I substitute the limit, I get 0 and the other gives me infinity, I can write it like this. I can write f times g as f over 1 over g. You see, at the end of the day, I'm trying to go back to quotient, all right, something over something. And or on the other hand, you can write it as g over 1 over f, all right? So you need to decide which of them. Remember, the ultimate goal of choosing between any of these two is to try and get to 0 over 0 or infinity over infinity, all right? That's the goal. Because before you apply L'Hopital rule, you must do the math. You must show me that it's an indeterminate product, and then rewrite it in one of these two forms, and then tell me now that now I now get an indeterminate form of 0 over 0, infinity over infinity. Then on top of the equality sign, just indicate you're doing L'Hopital, and then go ahead and apply your L'Hopital. All right. Let's look at this example. So limit as x tends to 0 on the positive side. Notice it here in the place of x, you're just going to get 0, right? And then what happened for ln x, right? For those of you who can see that you approach a minus infinity, I'll draw the ln sketch again. The ln sketch looks like this. It passes to 1 on the x-axis. So as x approaches 0 from the right, it means that you're walking along this guy and you come in this direction. You see heading towards minus infinity, all right? So we have 0 times minus infinity, all right? This qualifies for indeterminate product. Be careful, you can't apply L'Hopital rule because for indeterminate product, look at this. This is not L'Hopital rule. L'Hopital rule means I need some function divided by some function if I can apply L'Hopital rule, all right? So it doesn't qualify for L'Hopital rule. That means to rewrite it. And my best advice is whenever you see a ln involved, please just leave the ln at the top, right? Because if you try to take the ln at the bottom, you will differentiate forever and it will never end, all right? So try and always leave the ln at the top and never take a ln function at the bottom. Please never do that. So in this case, I leave the ln at the top and then I write x as 1 over x, all right? Remember, by writing it like this, I haven't changed the initial function. If you simplify ln x divided by 1 over x, it still gives you x times ln x, all right? You haven't changed anything. So then now let's take ln as x approaches 0 from the positive side. You know you're going to get minus infinity. And let's look at what happened at the bottom. As x approaches 0 from the positive 1 over x, notice you get infinity. There we go, it qualifies for L'Hopital. Remember I told you, L'Hopital you either get 0 over 0 or you get plus or minus infinity divided by plus or minus infinity. So we get minus infinity over infinity, so it qualifies for L'Hopital rule. And again, mention that you do L'Hopital by putting a little LH and then differentiate the top, differentiate the bottom. If you simplify, there we go, you get 0. All right. So when you get an indeterminate product, majority of the time, if you have a valid answer, you will get 0 as your answer, all right? And if it doesn't work out, you just get infinity. All right. Now let's see. Okay, so here they're just trying to explain what happens when we wrote this as. So if you choose to write this as x over 1 over ln x, there we go. That's exactly what I told you guys not to attempt, all right? If you choose to take a ln at the bottom, so if you make a mistake and you take a ln at the bottom, you know the derivative of 1 over ln x is, all right, is going to be some chain root and then ln x will appear again. So it becomes more and more complicated, all right? Please don't do that, all right? It gets more complicated. So ln function, leave it at the top, take any other function at the bottom. Most of the time that will save you time. And it's easy to know if you're making a mistake. If you differentiate and it keeps getting worse and worse and worse, then know you made the wrong choice. You took the wrong thing at the bottom and you left the wrong thing at the top. Now let's look at indeterminate difference, all right? Indeterminate difference, I'm looking at the limit as x approaches a of f of x minus g of x, and you get something that looks like this, all right? Infinity minus infinity. Now be careful. Don't get 0 minus 0 and tell me that that's an indeterminate difference, right? For indeterminate product, we say 0 times plus or minus infinity, or it can be plus or minus infinity times 0. Remember, multiplication is commutative, means that 0 can come first before the infinity, or infinity can come first before the 0. It doesn't matter as long as you have multiplication. Now, for indeterminate difference, focus is infinity minus infinity, right? Up, because it minus infinity, all right? As long as I see infinity minus infinity, it works. Not 0 minus 0, please, because 0 minus 0 is 0. It's not an indeterminate form, all right? Now, how do we get it to L'Hopital? Because L'Hopital, for us to apply L'Hopital, we need to get it to 0 by 0 or over infinity. The best idea is to try and bring everything to a common factor. So factorize as far as you can, rationalize if you can. So do all the maths, all right, and try and get it to some function f of x divided by some function g of x, all right. I'm not saying that f of x minus g of x will become f of x or g of x. Let me just use another variable, so you end up with some h of x over some k of x, all right. So try and simplify as much as possible to get it as some function divided by some function and see if you get 0 by 0 or infinity. So let's look at this example. Wow, this is a nice one. You see what I was trying to tell you? If you plug in 1 there, you get ln of 1 is 0, so you get 1 over infinity, 1 over infinity. Let's look at it closely. This is 1 from the positive side, so it's fine. So you get 1 over 0 from the positive side, which is going to be positive infinity, be careful. And here also you get 1 over 0, you still get infinity. So this qualifies for indeterminate difference, all right? Infinity minus infinity. And look at what they did here. They just find the LCD, all right? Common denominator, so you have ln x times x minus 1. And then try and substitute again your 1. Let's see what happens now. So at the top, you get 1 minus 1 is 0, minus ln of 1, which is 0. So I have 0 there at the top. At the bottom, I have 1 minus 1, which is 0. Obviously, 0 times some infinity value there is 0. You see, it qualifies for L'Hopital, all right? And they I'll just put LH. You see, this step they do in L'Hopital, differentiate the top, differentiate everything at the bottom. Simplify as much as possible. You see, another thing is when you differentiate, simplify as much as you can. Again, you get 0 over 0. So if you do that, you end up with 0 over 0. And then you need to apply L'Hopital again. You end up with this. And if you simplify and you substitute, you end up with a half. All right. So it doesn't matter how many times you have to do L'Hopital, but once you keep getting 0 by 0 or infinity, you keep going, all right? Keep applying L'Hopital. Obviously, I will not ask you a question where you have to apply L'Hopital 5 times because that would also take all your time in it. But if you keep in mind that it can go up to 2 times or sometimes even 3, all right? And then indeterminate powers, all right? Here, there's so many possibilities. I will show you now. If you can get 0 raised to the power 0, all right, this is actually infinity raised to the power 0, all right? So you have 0 raised to the power 0, you have infinity raised to the power 0, and you have 1 raised to the power infinity, all right? Once you see this, you know you're talking about indeterminate powers. And the way they're going to ask you the question, you're going to tell that this is what they're trying to test, all right? So keep in mind 0 raised to the power 0, infinity raised to the power 0, and 1 raised to the power infinity. All right, so you end up with something like this: f of x raised to the power g of x. The idea is you let y to be that whole limit, and then you lean both sides. All right, it almost applies like when I showed you guys logarithmic differentiation, where you start by letting y be the function, then you lean both sides to simplify. So it's more or less the same idea. All right, and once you lean both sides, the right hand side will give you an indeterminate product, and then from there you know what to do when you have indeterminate product. You write 1 as a reciprocal, right? You end up with some function divided by some function. So let's see an example. Look at this, right? Once you see a function raised to some function, keep in mind I'm testing you indeterminate powers, all right? How does it work? If I put 0 in there, so 1 plus sine of 0, so remember sine of 0 is just 0. So you have 1. And what is cot of 0? Remember, cot of 0 is 1 over tan of 0. And tan of 0, you know, is 0. So 1 over 0 is infinity. So you end up with 1 raised to the infinity, which is an indeterminate power. Right? Remember, the indeterminate power is 0 to the power 0, infinity to the power 0, and 1 to the power infinity. So 1 to the power infinity qualifies as an indeterminate power. Now, once you identify this, you let y to be this whole function. You see what they're doing there. They let y to be that whole function. And they just lean both sides. You lean both sides. This power here will come in front of the lean. All right. So you end up with cot coming in front of the lean. Or you can just write it as lean of 1 plus sine 4x over tan. Remember, cot is 1 over tan. So if you write it like this, it makes life easy because you now have a function over a function. And let's now see, you apply limits. Very important, you take the limit. Remember, I asked you for limit as x approaches 0 from the right. So take limit as x approaches 0 from the right, on the left-hand side as well as on the right-hand side, all right? So ignore the left-hand side for now. Let's try and simplify the right-hand side. On the right-hand side, if I put in 0, I get ln of 1 plus 0, which is just ln of 1, and ln of 1 is 0. At the bottom, tan of 0, you know, is 0. So what is the form? 0 over 0. Does that qualify for L'Hopital? Yes. So here we do L'Hopital. And you see what they're doing? They differentiated the ln of 1 plus sine 4x. And they differentiated tan at the bottom. Give them 6 squared. And obviously, if you substitute your x tends to 0, you just get 4. So it's easy as that. All right. But be careful you're not done. Majority of the time when we ask in the test, people stop here. When they get this 4, they're like, I'm done. I have an answer. You're not done because you now have the limit x approaches 0 from the right of a ln of y to be equals to 4. Then you want the limit as x approaches 0 of y, which is the function that I asked you, all right? And how do you get that? You need to raise both sides to the power of e, right? So if I have ln of y equals to some number 4, and I just want to find what y is, obviously the idea is to raise both sides to the power of e, right? So you say e to the power ln of y and e to the power 4. So you can see what they're doing there. Therefore, this limit that they ask you will just be the limit as x approaches 0 from the first of y. And y is the same as e to the power ln of y. So it's the same as me just raising the left hand side to the power of e, and then on the right hand side you just have e to the power 4. So whenever you have an indeterminate power, your final answer is going to be e raised to that answer that you got, all right? So if you simplify that limit and you get 4, for example, your final answer will just be e to the power 4, all right? And how do we do that? You raise both sides to the power of e. And that marks the end of this lecture, all right? Any question? Yes, you can go ahead and question.
Jose, how are you?
Good, good. How are you?
Say, I need I'm fine, I'm fine. I just need clarification that you are saying that 1 over 0 is infinity.
Yes. That's infinity. If you have a calculator with you, punch 1 over 0, right? Error, when you see error in a calculator, it means undefined. It's infinity, right? So 1 over 0 depends on what direction you're coming from. If it's 0 from the left, you're going to get minus infinity. From the right, you're going to get positive infinity. So yes, 1 over 0 from the right is positive infinity. All right. Any other question? And for those of you who are still surprised that 1 over 0 is infinity, I showed you that we did that a couple of weeks back when we were trying to divide 1 over, we started with 0.1, and then we went to 1 over 0.01 and so on. Notice as this number keeps getting small, the output you're getting is very big, all right? If I give you 1 over 1 divided by 0.00000, let's say 20 naught and 1, that will give you some very large value in the billions. All right, so you see that the smaller the denominator gets, if you take reciprocal, then the infinitely large your output is going to be. So in summary, we just say 1 over, what's the smallest you can get at the bottom? If we're looking at the positive side, we're not considering the negative side. It's just 0, all right? Something strictly close to 0. And there we just say infinity, all right? So that is the whole idea. So if you take 1 divided by 0.1, it's getting big, so it becomes 10. 1 divided by 0.01, it gets to 100, and it keeps going in that order. 1 divided by 0.0001 in tens of thousands, it gets to hundreds of thousands, billions and billions, to a point where you can't even compute. And already, once you hit 1.00001, that's approximately equal to 0. That's why we just say 1 over 0 is equal to infinity. All right.